Hi, my name is Gary Millette. I'm your instructor for EET-250 Control System Theory. This is the spring of 2023, and the title of this presentation is Introduction to the Technology of the Fourth Generation of Control Systems. So let's get going. First off, there are two references that are on the Blackboard website. Reference number one is Modern Control Technology Components and Systems by Killian. That's on the far right. Reference number two is Instrumentation and Process Control by Terry Bartlett. So those are both on the Blackboard website, and for this particular presentation I ask you to take a look at Chapter 1 of both of these texts. So we're going to start by looking at the classic control system block diagram. So here you can see this block diagram. There's a thing called a controller, an actuator, and then the process. Now, the input to the controller is what's called the set point. The output of the whole thing is the controlled variable, and you might say the set point's the desired result. The control is the electronic intelligence. The actuator is the mechanism that's going to make everything work. The process is the physical system you're trying to control, and the control variable is a measurable result. So, as can be seen from the figure, the classic control system is given an input, that's a set point, and the system attempts to provide an output that is consistent with the settings or setting of the input. Now, if we take a look at this and kind of go deeper into each one of these blocks, before that we should give you an example, a simple but fairly universal example of this type of control system is the throttle, that is the gas pedal of a modern automobile. Actually, the gas pedal is more correctly known as a throttle position sensor, or TPS, in modern cars. What about the set point? The set point's the desired result, and that could be all these different things here: temperature, speed, pressure, voltage, current, height, flow rate, and so forth. For a more complex control system, the set point can take on more complex constructs. It could be a machined or milled part, an automated process, an automatic pilot, autonomous driverless cars, autonomous machines like robots, pilotless drones, and so forth. So again, maybe the set point is you launch a drone, and the drone comes back to where it was originally launched from using GPS. What about the controller, or the electronic intelligence? Well, that's the device that monitors and physically alters the operating conditions of a given dynamic system. Historically, the controller typically used some form of mechanical, hydraulic, pneumatic, or electronic means to implement its function. Today, it is commonplace to incorporate a computer or microcontroller to perform this function. Moving on, we should talk about the actuator. This is basically a type of motor used for moving or controlling a mechanism or a system. This could be a familiar electric motor with its associated mechanical gears and worm screws. That'll be covered later in the course, or some type of micro electromechanical or MEMS device used in a medical implant device, we'll say. What about the process? The process is the physical system that's being controlled. There are several different types of processes. They can be called discrete, batch, continuous, and hybrid combinations of the prior ones I just mentioned. What about this arrow that goes into the process called disturbance? Well, anything that has an influence upon the state of the physical system is a disturbance. If this was a communication systems course, we would call this noise. And the last thing, the control variable, that is a measurable result of the physical process. And again, examples would be temperature, pressure, height, speed, position, voltage, current, flow rate, and so forth. A more complex control system, such as a car electronic fuel injection or EFI system, provides efficiency in miles per gallon, as well as also smog reduction or pollution reduction. So we might ask the question, what is an enhanced or smart system? Some examples would be any system that employs an embedded microcontroller tends to be considered an enhanced or smart system. Example would be your microwave oven. Car safety features like tire pressure monitors, electronic stability control or ESC, and AEB, automatic emergency braking, would be smart systems. Other examples, intelligent transportation systems, RFID chips, especially Generation 2 chips, and something like an Easy Pass transponder as you drive down the turnpike. What about system connectivity? Many recently produced enhanced systems employ smart sensors and actuators, and in many instances they use wireless networking technology to send messages to enhance the system. However, these systems are not necessarily complete feedback loops. And you might note recent car commercials on TV showing smart collision avoidance systems, again this AEB acronym. So going back to our classic control system, I've now added the term open loop control systems to the block diagram I had previously. Now in this one, the open loop control system has no mechanism to check whether or not the controlled variables match the set point. Notice there's no feedback. Examples of open loop systems would be the common street light that turns off and on with the ambient light intensity. And I'm sure you've driven down the highway at some time and seen street lights on during the day or street lights that are not on at night. And it's not necessarily that their bulbs have burned out. It might be that the sensor which turns it on and off is not functioning correctly. Again, these are called open loop control systems. We don't check whether things are actually doing what it's supposed to do. Now, the other type of classic control system is a closed loop control system. And notice we've added another block, and that block is called sensor or sensors, and is a feedback path that goes back to an additional, in this case, circle as opposed to a block, and that's a comparator. So what we do is we check the output to the set point and produce some error signal that goes to the controller if the control variable and the set point are not the same. So this type of control system uses a sensor or sensors to measure the control variable to see whether or not it matches the set point value. Most modern day control systems use this type of technology. Example, cooking oven or home heating system. The comparator compares the set point value to the measured value of the control variable and produces an error signal for the control. I've already said that. The sensor or sensors measure the control variable. I already said that. So that's the details of how that works. Now, it turns out any control system will have a transfer function. And a transfer function of a system is a mathematical relationship between the input signal and the output signal. So, shown in this equation, transfer function equals output over input. The notion of a transfer function of an electronic system is quite common. Amplifiers are an example of that. The relationship between the input signal and the output signal of an amplifier is commonly known as the gain of the amplifier. Of course, the gain of an amplifier will also be a function of the input frequency, so the transfer function or gain will be a function of several variables. The transfer function of a filter is known as its frequency response, just to give you some examples. In control system theory, transfer functions are used to describe the relationship of the variables in the control system. Oftentimes, the input variable is not the same as the output variable. For example, volts in, RPM out, if we had a motor. This is not a problem as long as one is careful with the units. The transfer function can be a function of time. That is, it varies with time or changes with time. We'll usually only consider steady state transfer functions. That is, they're time invariant. So we have a little more sophisticated equation. The transfer function is steady state. say is equal to the gain, which is equal to steady state output over steady state input. How about a transfer function of a cascaded system? So here I show a block diagram of a cascaded system of transfer function 1, 2, and 3, represented by 3 blocks. The transfer function of a cascaded system is given by the multiplication of the individual transfer functions. And the transfer function total is shown in equation form there as transfer function total is transfer function 1 times transfer function 2 times transfer function 3. Note again that the output does not need to have the same units as the input. In other words, apples and oranges are okay in this case. What about a closed loop system? Well, here's a diagram that shows block A and block B, and each one of those would have a transfer function. It says here the transfer function of a closed loop system is given by, well, the total transfer function is A divided by 1 plus A times B. And notice there's also a comparator there that takes and compares the output and the input. So this last fact that the transfer function total is A divided by 1 plus AB, it is the basis for the operation of electronic systems known as op-amps. And you sometime in your course of study here at STIC will study op-amps. It turns out, interesting fact here, an AT&T Bell Labs worker came up with the notion of negative feedback in amplifiers in the mid-1930s. Amazingly, it hadn't been tried until then. It turns out, interestingly enough, that negative feedback makes all the characteristics of an amplifier better. This guy was once on a ferry going from Staten Island or something to New York City, and he wrote this down in the back of a New York Times or something like that. But it wasn't until the mid-1930s, and we had amplifiers. You know, vacuum tubes were around during the 1910s, so about 20 years worth of technology, and nobody ever came up with a negative feedback amplifier. So here's a transfer function example. This is out of one of those reference books I showed you. So on the left-hand side we have a motor, then we have some gears in the middle, and then a winch. So what happens here is the motor has a transfer function. I have V in that runs the motor, and then I have a velocity of inches per minute on the winch. And it turns out that the transfer function on the left hand, well, the motor times the gears times the winch, we can come up with a total system transfer function, volts in and velocity out. Now, what about digital control systems? Just about everything today is digital, so we have taken and improved control systems from analog systems to digital control systems. So a digital control system uses digital to analog converters, which are called DACs, and analog to digital converters, or ADACs, ADCs. In these systems, analog data from the sensors is transformed into digital data so that it can be dealt with by a digital controller. Typically a microcontroller, microprocessor, or in some cases a digital computer. Now the era is a binary number that's converted into an analog value by the DAC in this system. Now, actually presently today you discover that very often the sensors will put out a digital signal. The ADC function is built into the sensor, and there's no need for a DAC coming out of the controller because that's built into the controller. So those things have probably merged into the blocks that they're closest to. Again, here we show this new line here into the controller, and it's bidirectional, notice, so that's an interface connection. So today we add communications interfaces to our digital closed loop control systems. With this interface we can now create cyber physical control systems that are enabled by the internet. And we'll talk about what cyber physical control systems are. Now, classifications of classic control systems. Well, process control, classical example of this is an electric oven. So you have a set point, desired temperature like high or medium or something like that. You have a heating element in the back of the oven chamber for the, say, electric oven or gas oven. There's a thermocouple that measures the actual temperature. You feed that back and compare it versus the set point, and you turn the heating element off or on or lower or higher depending on whether the temperature is correct or not. Here's another process control example. Mixing paint. We have manual controls here. You see we have blue and yellow, and we're going to mix those together. So we have flow control valves 1 and 2, and we get green if we're very careful with how we mix those together. Here's the same thing with mixing paint with automatic control. Now what happens, we have flow valves that are run by, say, an electronic flow sensor that's inside the pipes there, and this automatic flow control probably gives you better green paint than just mixing it together manually. Finally, we have automatic color control here, where notice in this case we have color sensors, and the feedback from the color sensors goes to the flow control. So things have been getting more and more sophisticated. Here, for instance, is an example of a pH process control, and notice there's a stock pump, an acid pump, and a caustic pump, and a caustic vat there. And it turns out that we can take and control the flow rates of all those things and get whatever pH we want out of this process. Here's another process control system, and you can see this one starts, it's got arrows that indicate the various processes, how they go sequentially and so forth, and then at the very end there's several different outputs of this process. So we have different approaches to multi-process control. We can have multiple controllers. So in this case here you see local process 1, local process 2, local process 3, and we have 3 separate controllers to take and control each one of those separate processes. That's called individual local controllers. Here's direct computer control, a computer acting as 3 controllers. So we had those 3 local processes before, but now we have one main central computer that controls everything. And then we have distributed computer control, where we have a supervisory computer and 3 different controllers, and again 3 different local processes. This is somewhat similar to how building automation occurs, but we'll talk about that later. Here's a sequentially controlled system. This is a classic washing machine sequence, where we start off with filling the tub, agitating the clothes. Looks like we then drain the tub, then we spin it, then we refill it, and do the same operations over again for a second cycle. And of course, the sequentially controlled washing machine was not controlled electronically, but instead was mechanical in nature. That is the classic washing machine. A clock-driven sandwich of cams with high and low spots activated relays, which activated valves and motors to provide the washing cycle. Cycle was fixed, only mattered where it started. So here's one of those sequentially controlled washing machine controllers. Today's washer and drivers have embedded control, that is microcontrollers, to facilitate their operation. No longer do they use mechanical parts like the one shown here that can wear out or break. Of course, electronic systems can malfunction. Here's classic motion control, a servo mechanism. In this case, what happens, you turn the control panel to say east, and the antenna will turn itself to be east. And notice it's got a feedback position sensor, so it's a classic closed loop process. Here's classic numerical control. In this case, you might notice there are 3 X, Y, and Z motors, so that table can be moved in 3 dimensions. We have a motor with a tool, cutting tool, and a workpiece, and so we can take and mill that part to whatever we want it to look like. Digital numerical control, here's a laser cutter. Robotics, here's pick and place. Notice the X, Y, and Z axis here, and we have different motions that we can have with the different arms. And we call that degrees of freedom sometimes. Here's some robotics pick and place examples. I like the one on the left because that's where all the garbage seems to be picked up in this local area in Western Mass. A truck coming along and dumping either the waste or the recyclables into a truck. On the right hand side we have industrial robotics pick and place example. Here's some more pick and place examples. We have cups on the right hand side, and looks like spools of something, wire maybe, or some other type of product on the left hand side being packed. Here's a large industrial robot. This diagram shows all the degrees of freedom of motion for this large industrial robot, and notice it has to have a complicated controller. This one is an interesting one. You can find this on YouTube video. Link shown on this slide gives a good view how a Tesla automobile is put together using manufacturing robots. And you can see actually there's an assembly line there with lots of robots that they can put this thing together. Now, for a lot of what we do with control technology today, we use sensor network technology. For the past decade, researchers in many diverse fields have been exploring the possibilities of the use of application-specific sensor networks to perform a host of various tasks. Typically, a sensor network is a deployment of an assemblage of complex sensors with embedded, or what we call ambient intelligence, and advanced actuators. These sensors and actuators are linked together with modern data transport and networking technologies. By that we mean locally by LANs, PANs, which are personal area networks, NANs, neighborhood area networks, BANs, which are building area networks, etc., and over distances via the internet. This is known as IP, or Internet Protocol Technology. Excuse me. The newest buzzword for these types of systems is cyber physical systems. You might want to think the smart grid, although if you're not familiar with the smart grid, that was how a big push back 10 years ago, we were going to make the electric grid intelligent. Today, sensors and actuators have become smart or intelligent. That is, they may consist of an embedded controller that is able to process data, save error correction or calibration data, and if appropriate, alter or change the sensor or actuator functions. As mentioned previously, this smart sensor or actuator will be networked. That is, it will have a physical data connection to a computer network. Today, there are many applications where the system to be controlled or enhanced is geographically large. Things like process control systems, building automation systems, transportation systems, surveillance systems, telecommunications networks, smart grid, and so forth. These types of control systems typically require a computer network that links the subsystem to a central controller. Sensor networks may be wireline based or wireless or a combination of both. IEEE 802.15.4 wireless technology, aka also known as Zigbee, is getting a great deal of attention for wireless sensor networks, and various field bus networks are typically used as wireline networks. Industrial Ethernet has also drawn a great deal of interest from various industrial fields. We have a version of that that's recently been standardized. Also, people in the industrial field talk about Industry 4.0 and IIoT. These are new buzzwords. IIoT stands for the Industrial Internet of Things. So, what's Industry 4.0? This little graphic shows the 4 stages of Industrial Revolution according to Bosch. Stage 1 was the late 18th century. First mechanized manufacturing equipment powered by water and steam. And it's got a date there of 1784, first mechanical loom. Early 20th century was stage 2, or era 2. Introduction of mass production with the help of electrical power. So it says 1870, first assembly line, slaughterhouse in Cincinnati. Stage 3, early 1970s, or Industry 3.0, use of electronics and computers to automate manufacturing worldwide. And it's got a date of 1969, use of electronics and computers to automate manufacturing worldwide. Stage 4, or Industry 4.0, cyber physical systems. Real objects and virtual processes are interlinked. Connected industry, smart factories. So what about future sensor networks? Most future sensor network applications are envisioned to rely on wireless connectivity. We could talk about networked robots, networked vehicles, biomedical monitoring for health, networked infrastructure, cognitive radio, and so on. And finally here, nanotechnology applications for healthcare will need to be networked. Other intelligence infrastructure / cyber physical system applications are possible in just about any technology space. In other words, anything one can imagine. So control systems have expanded to go to any type of system that would be enhanced by a smart control system. That's it for this one.